Today, the talk will be by Professor Azzedine of the Laboratory of Chemical Formation Laboratory in Toulouse, France. Let me introduce very briefly Professor Azzedine. He's an author of over 260 articles in international journals, including 10 Impartido reviews, 24 VIP quarterly articles, and 13 other articles. 4 book chapters and 11 patents. Azzedine Bousseksou publication has been cited more than 8,000 times in the literature, with an H index of 51. These innovative, original, and impacting contributions can also be presented in around 80 international conferences and 30 invited seminars. More than 200 oral poster contributions, and he has organized 11 national and international conferences. He has several awards and honors, such as the Montpellier University Medal, won in 2014, the CNRS Excellence Distinction in France, several prizes from the French Chemical Society, the Korean Society, and so on. Please, let's thank Professor Azzedine and welcome here to the students and guests.
Okay, thank you, Luis, for the introduction. Thank you very much for the invitation. I'm very happy to be here. I know some people from this center, we had in the past some discussions, some exchanges. And I'm very happy to visit your center. So then, as Jose Luis told, we are CNRS laboratory in two CNRS laboratory. Our main point is to make molecules by using coordination chemistry. And the difference between the groups and the teams, it's in the properties of the molecules. So then we are belonging 3 institutions, CNRS, Université Paul Sabatier, and National Polytechnic in Toulouse. At the moment I'm heading this institute. So then concerning the properties of our molecules, you have properties in catalysis, in materials, in health. So then we are something like 300 members with 15 teams, okay? Each team has a leader, and you have something like 16 in the chemistry, coordination chemistry and catalysis. We have 7 teams in chemistry for materials, and we have 3 teams, chemistry and health. So then my team, it's this one here. So then we are working on materials, and then we are working especially on bistable molecular materials. So then what we want to do in the team, we want to make molecules that they are bistable, they are switchable. So then what we want to do, we want to make the synthesis in order to have the bistability, okay? So then we have work concerning the synthesis of such switchable molecules. We are dealing with thin films. You know, when you have switchable molecules, then you have many applications around. So then we need to have the thin films. So then we have work concerning making the thin films. And then we are doing physics, because these molecules are multifunctional molecules. So that means that when you have the switching, you have many properties changing. You have optical properties, the electrical properties, and even mechanical properties. So then we have in the group an action concerning the physics, solid-state physics, as spatiotemporal behaviors. We are working with nanodots, nanophotonic dots, and nanomechanical, and applications as photonic systems nano actuators and electronic devices as memories. So then this is the group, okay? So then as we are focusing on just the molecular biostability, so then in the group we have Lionel Salmon, who is present, who is dealing with the chemistry, so to make these molecules. And then we have Gabor Molnar, who is dealing with solid state measurements and the physics, okay? And then we have William Nicolas, who is the theoretician, and myself. So then we have a multidisciplinary team. We are all permanent, we have all permanent positions in the CNRS. And William, he is associate professor at the university. And then we try to deal with this together with these molecules in order to go from the synthesis until the integration of such molecules in devices. So we have several PhD students, we have 2 technicians and several postdocs. Okay, so then what means switchable molecular materials? So then what means then the speed crossover systems? We are synthesizing molecules that they have 2 spin states. Here it's low spin state, spin 0 for iron 2, and spin 2 for iron 2. So then you have these 2 states, spin 0 and spin 2. They are quite close in energy. Okay? They are so close in energy that they can be switched from one state to the other one by temperature, pressure, magnetic field, and light. Okay? The first part is to make molecules where you have 2 states which are very close in energy. Okay? And then if you wish to look at the energy of such molecule, it's the total energy, it's double potential. Okay? You have the low spin state and the high spin state, and the gap between the low spin and the high spin is just something close to KBT. So then when you have the switching from one state to the other one, because you have the change of the spin states, spin 0 to spin 2, okay, you can see, if you look at the magnetic properties, here is T as function of temperature, you can have a jump at critical temperature from one state to the other one, and then you even can have hysteresis loop, because molecules are interacting between them in a network, and the interactions has elastic origin of the cooperative interactions in the systems. And then you can have first order phase transition with hysteresis loop. So then when you go from one state to the other one, you have the spin state change. You can have also volume change. You can have the cell, the unit cell of the molecule changing by something like 30%. You have a huge change of the volume of the system. Why? Because when you go from the low spin state to the high spin state, you see here you are operating anti-bonding orbitals. And these orbitals are, of course, bigger. So now that means that if you go from one state to the other one, you have necessarily volume change. And then if you look at the electrical properties, you can have also a change of the electric properties by 12%. So then in the group, we are studying the thermochromic properties. Okay, here it's, for example, our sample here. You also, because you have huge electronic changes between one state to the other one and the volume change, and then the color of the system may change from pink to yellow to white reversibly. Okay? So then in the group we are studying the thermochromic, photochromic, piezochromic, and magnetochromic properties of these molecules. And then because we have many, several changes in the properties, here is magnetic changes, here is the volume change, and here is the electrical change, here is the optical change. That means that we can use such switchable molecules into devices as memories, sensors, electronic photonic devices. And then I will show you some devices using such molecules in nanoelectronics, nanophotonics, and even nanomechanics. Okay? So in order to do this, of course, we have in the lab several characterizations, technical equipments. This is the magnetic equipment. This is the optical and fast, and so that you have IFM coupled with Raman spectroscopy and optical techniques. We have X-ray diffractions as function of temperature and even pressure and light. Okay, and then we have some photonic, some nanocirculations in the group, and some equipments in the transport for the electric results. So then, of course, this field is quite hot at the moment. We have many collaborations over the world concerning the chemistry, the nanotechnology, the high pressure, high magnetic field, Raman spectroscopy, and theory in Europe, in the US, and in Asia, and even with several groups here in Mexico. So I would say that the spin crossover phenomenon is quite old phenomenon. Okay, it started in 1931 when people tell something like 2 or 3, where people were dealing with only the properties of a single molecule. So then I can call it molecular period. In that period, people, they were just synthesizing the molecules and trying to understand the properties of the molecules, the switchable molecules. And then it was a period where the synthesis were very, very, very hard. And then you have, after that, the nanoparticle periods, because people wanted to know how they make integration, how we can have bigger systems where we have this switchability in order to integrate them into devices. And then, of course, the physicists started by studying the switching, the spatio-temporal period, where we were trying to see, as function of time and space over the crystal, how the phenomenon behaves, because you have switching, and then you have a lot of dynamics, and then spatial propagation, and then there is many spatio-temporal approaches was done at that period since 2006. And then, of course, because of the integration to make devices, we need to make thin films, and then this period started in 2006. And then after that, we have since 2013 hybrid system periods, where people were looking for synergetic effects between spin crossover and something else, like luminescence, like many other properties, where we try to see synergetic effects between spin crossover and other molecules. And of course, you have this device and integration period, which started already since 1998. So then, for the molecular period, you have here all the main papers was published in the field. I would like to say that at that period, the end of this period was ended by a book edited by Philip Wittlich, and the European network, where I was involved there with my team and the laboratory. And you have here one very nice review, topics in current chemistry. And then in these topics, you have all the molecular and synthesis strategies published in these papers. So then, during this period, to understand the phenomenon, the spin crossover phenomenon, of course, if you look at the molecular materials, it's a repetition of one molecule through hydrogen bonds and through bonds, okay? And then the question is that at that period, we were also studying the properties of the molecules. I would like to say that the local properties are today well known. I mean the structures, the vibrational properties, the theoretical calculations. I think we know mainly all the molecular properties of switchable molecules. And then, of course, if you say that each molecule it's a double potential. That means that at the solid state, your molecular, switchable molecular material or spin crossover material, it's a network of double potentials, okay? Because each molecule can be represented by double potential, and then in the network you have connections, you have elastic connections, and then you have a network of bistable of double potentials interacting. And then you can think about the transmission of the information, the propagation of the switching through the crystal, and you can see many, you can think about many approaches concerning the switchable materials. Theoretically talking, if we wish to synthesize this period, if we say that spin crossover system, the molecule is double potential, we can use Hamiltonian, which is one spin fictitious system where it describes just the gap energy here. And if you go to the network, to the crystal, you have to add the interactions by J sigma sigma, which is Ising-like model formalism, where J here has elastic property, here elastic origin. And then, of course, because when you go from one state to the other one, the volume of the molecules changes, so then you have to add the vibrational properties of each state. So then spin crossover system, it's just the addition of these three terms, these three energies, and then you can describe your system by this methodology. So then if we take an example, for example, this molecule here, in this molecule, we have strong comparative interactions. I mean that we have strong coupling between molecules, strong elastic coupling between molecules. If you have such a case, and then if you try to solve your Hamiltonian, you will find that you have first order phase transition in this system. And if you measure the proportion of high spin as function of comparator, you will see that you will have a hysteresis loop, okay, like that, okay? And then in this system you have a hysteresis loop. When we have a hysteresis loop, that means that at fixed temperature, you can have two states, 0, 1, okay? You have the memory effect in the system, because at fixed temperature, you can have two states, and then you can reach one state or the other one, and then the occupation of one state depends on its history, okay? And then as I told you, you can have a huge change of the optical properties. You can go for example, for this system from white to pink, change of spin, change of the volume. So then, if you make some experiments to see this color change, for example, if you prepare your system at this temperature, at 140 for example, and if you try to cross the hysteresis loop like that, so then you have just to heat the system, okay? So then at this state, of course, the system is in the low spin state, it's pink here, and then if you heat the system, okay, the system will change its colors slowly till you go to the white color, and then the system is in high spin form, and if you come back, so then you will cross the hysteresis loop, and then the color of the system will change to the white, the pink color, which is the color of the high spin, the low spin form. That means that just by temperature, you can switch reversibly from one state to the other one by just changing the temperature. Okay? So, if you wish to understand what is the mechanism of switching at the molecular level, what we say that the entropy is a driving force. If, for example, we take a system where you don't have hysteresis, the interactions are quite quick, weak. So then, if you prepare your system in the low spin state here, okay, and you look to the structure of your system, it's in the low spin state, so then all the molecules are in the low spin, you have contracted molecules, low volume, okay? If you look at the free energy of this system, okay, you have at this temperature the low spin state, which is more stable, okay, and then you have double potential. So then, if you look at the free energy of the system, which is delta G equal delta H minus T delta S, you see that here the enthalpy of the system is constant. The entropy change, it's electronic or vibrational, which is constant. The unique parameters here, you have its temperature. If you change the temperature, for example, so then if you increase, for example, the temperature, you will increase this part, so then you will destabilize the system, okay? And then, for example, if you heat your system, so then you will see to your double potential, you will destabilize the low spin state to the high spin form, and then you switch the system. If you continue heating your system, you will see that you are destabilizing your double potential till the total conversion. Of course, the system is reversible. If you come back, I mean, if you cool your system, you will destabilize your double potential on the other side, and then you switch on the other part. So then, just by temperature, through the entropy, you can have your switching, and then we say that the switching, the molecular switching, is driven by the entropy change of the system. So this is to explain how what is the mechanism of the switching. So then, of course, we are interested in cooperative systems where the connections, the interactions between molecules are strong enough, and then we need to have the hysteresis loop, and of course we need to have systems where the conversion, where the crossover is at room temperature. If you see to this polymer coordination polymer system, you have the ion here, you have here nitrogen, carbon, nickel, and then carbon, nitrogen, and iron. It's polymeric, it's 2D system, okay? And then the plants here are connected by this bond, which is the pyrazine ring. And this is 3D coordination material systems, we can say it like that. And then because the elastic interaction between the ions are strong enough, because you have real bonding here which are quite strong, you have strong elastic interactions. In that case, if you measure the chi-T as function of temperature, you will see that the crossover, spin crossover is at room temperature here, you see, and then you have also a hysteresis loop in the system, so then you have a memory effect at room temperature, okay? So then, of course, when you have such system, you need to see how we can address this system, how we can write information, how we can switch it quickly and easily, okay? So then we wanted to see if by light, with, for example, laser beam, pulsed laser beam, at the nanosecond scale, we can switch this system. I will show you that it is possible to switch reversibly this system between low spin to the high spin by just pulses, by 2 pulses of 8 nanoseconds. I will show you this and the mechanism of this effect. So then if you go to the Hamiltonian I have shown you before, and you look the systems where the cooperative interactions is strong enough. So then if you analyze the hysteresis loop, you will see that you have 4 regions. You have this one, this one, this one, and this one. What you can see also, you can see that you have this region which is high spin form, spin 2 form, and it's metastable. And then you have here, this region here, which is low spin form, and it's metastable. You have 2 metastable states with 2 different spins. That means that if you are metastable, if you are here, if you find a way how to give energy to your system, so then you expect to switch the system from the metastable to the stable one. And if you are here, just around the critical temperature, which is metastable in the high spin form, you expect that if you can find good energy to give it to your system, to switch your system from metastable state to the stable one, that means that in theory, you can go from spin 0 to spin 2, and from spin 2 to spin 0, reversibly around the critical temperature. So then, this is the theory. So then, in order to find the right energy to send into the system, we looked at optical properties. If you look to the optical properties in both states, you see that the green light, for example, it's absorbed either by the low spin or the high spin form. Okay, this is how we can send our energy. And then, of course, if you send this energy and you want to see if you have switched effectively your system, you need to measure it. So then if you look at the Raman spectroscopy of this system here, you see that from low spin to the high spin, you have here a Raman shift of more than 30 wave numbers. That means that in principle, you can switch your system from low spin to the high spin reversibly by sending green light, by measuring the Raman spectroscopy, you expect to follow the switching. So then we did these experiments. We took two lasers, red for measuring the Raman spectroscopy, and green light, pulsed green light to send the energy to switch the system. So then we have this protocol here in order to do these experiments, which is here. Okay, so then here is the experiments. As I told you, we have to see in 4 places here. Here it's low spin, here it's high spin. So then if you are here, if you prepare your system here in the point A, where you are in the low spin form, and then you look at the Raman spectroscopy, you see that the spectrum is pure low spin state. You have nothing in the high spin form. Okay? The system is 100% in the low spin state. If you send your pulse, you see by Raman spectroscopy, you go from this spectrum to this one, which means that you have no low spin state, and then you have generated high spin form. That means that you are going from the point A to the point B, okay, by sending your first pulse. And now, if you fix your temperature in the high spin form in the metastable state, you look at the Raman spectroscopy, you see that here, okay, the system is in the high spin form, nothing in the low spin form. If you send your green pulse, okay, you see that you go from this spectrum to this one, where you transform your system from complete high spin to complete low spin. That means that you are going from this state to this one. So you see, this is the demonstration by Raman spectroscopy that at room temperature, with 2 pulses, you can write or erase your information by just 2 pulses at room temperature, which is quite interesting and quite important. Okay, so then after this, there is a period of solid state physics period where we wanted to see when you have this switching through the crystal, what is the mechanism? Do we have a random appearance of the high spin form when you switch your temperature, or do you have an effect where you have nucleation and growth, because you have domains and then you have propagation? 2 questions. Is it a random following Boltzmann statistics, or is it nucleation and growth process? So we wanted to see this, and then the period, the spatio-temporal period started. So then theoretically, if we use the model I have shown you, the model tells us that when you go from the low speed state to the high speed state, you expect that you are going by nucleation and growth process. Okay, this is the model. And then we wanted to see this by using Raman spectroscopy, by imaging the crystal. If we take crystal and then we try to do imaging by using Raman spectroscopy with this molecule here. So then you see here, the low speed state has, we take, when we have the low speed state, we take the green color, and when it's the high speed state, we take the pink color. So then we image the crystal by Raman spectroscopy as function as temperature in the region where you have the switching. What you can see here, the system here, it's at 235 in the low speed. When you increase your temperature, you see the appearance of some domains of high spin form. And when you continue heating your system, you see the domain of high spin state increases till the total conversions. This is the demonstration that spectroscopy we can demonstrate that when you have the switching through the temperature switching through the region where the system is switched, the process is nucleation and growth process. Okay. So then here it's we wanted to see it by optically by using polarizers, the crystal through crossed polarizers, and this is the experiments, the optical experiments through the microscope, and then we wanted to see this nucleation and growth optically. Okay, so then you see this is the crystal. If we increase the temperature, you see that we can optically also see that we have the nucleation and growth. You see, this system is in low spin form here. When the temperature increases, you see the system is switched by a process as nucleation and growth. And what we wanted to see if any defects we can generate on the crystal has an effect on the nucleation, on the growth, on the propagation of the spin state in the system. So then we used exactly the same crystal in the same condition. You have seen in the previous one that you have the nucleation and growth in this direction here, and this is the crystal, the same crystal. We did exactly the same experiments, but the difference is that we put here a defect by just ablation. Okay? When we do this, you see that and then we measure the propagation optically. You see that now the nucleation and growth started from the defects and goes in the other directions. Okay? That means that you have your crystal. At the beginning, you have the nucleation, the propagation of the spin state in one direction. You put defect here, and then the propagation changes its direction. So then it's propagating in the other direction. That means that artificially, if you generate defects in your crystals, you expect to control the nucleation and growth process. Okay? So, and then after that, because we have the materials, we know how we can switch them, we can address them, we know the mechanism of the system, for example, the spatio-temporal analysis, and then we wanted to have materials in order to integrate them into devices. There is two kinds of materials. You have nanoparticles. Why nanoparticles? Because we wanted to study the effect of the size of the nanoparticles on the phenomenon. Why? Because as I told you, the interaction between molecules is elastic. That means that it's elastic, yes. And then your coupling depends on the elasticity and also on the number of the neighbors. Okay? If you take, for example, a system where you decrease the size, you are looking to see what is the effect of reducing the size of the nanoparticles of these interactions on the phenomenon. You expect so then to go from first order phase transition to just gradual transition, and then we wanted to see this experimentally, this phenomenon. Okay, so the nanoparticle period. So then the chemistry of this part is coordinated by Yonat Salman, he is present. So then we synthesized in the group nanoparticles of spin crossover. So then the approach is to use the reverse micelle techniques by using surfactants and then by playing with the concentration. And then you have two reactors, two nano or micro reactors here. You have here the iron salt and the ligand, and you have here the nickel salt. And then if you combine this, you have your reaction here. And then by playing by the concentration, etc., so then you can have nanoparticles. And then depends on the temperature, concentrations of the surfactants, etc., you can play, you can control the size and the shape of your nanoparticles. You see here, you have 2 nanometers nanoparticles. You can have 100 square nanoparticles. You can have different forms. Okay? So then this is very nice because it allowed us to study the effect of the reduction of the size of our materials on the spectroscopy. You see here, this is the experimental measurement here, KT as function of temperature for different sizes. Okay? You see that in the bulk material, macroscopic materials, if you have hysteresis loop, first order phase transition hysteresis, if you decrease your size, you see when you go from the bulk material to 120 nanometers, you are cutting the interactions, so then you will lose your hysteresis loop. You see, you have gradual crossover. What it was strange and very interesting in such experiments is that when you go to very low dimensions, like 2 nanometers, you see that the hysteresis appears again. It reappears. So then, from this region to this one, in 2 nanometers sizes, you know you have no bulk. Okay, that means that we have some surface effects, and then we look at by mass power spectroscopy to the Dubai temperature, for example, which measures the elasticity and the rigidity of the system because of the surface effects. Because of the surface effects, so then the rigidity of the system increases at very low temperature. And because the elasticity through the surface effect increases, that means that the cooperative interactions in the system increases again. So that means that when you go from bulk to nanometric systems, you cut the interactions, okay, and then you lose the hysteresis. When you still reduce your system because of the system, because of the surface effect, because of the elasticity which diverges at very low dimensions, so then your hysteresis appears again. This was very, very exciting results. That means that by stability, the hysteresis loop can be seen even at 2 or 1 nanometer nanoparticles. Okay? This is quite important for the density of the storage if you use the systems in devices. And then, of course, after the nanoparticles and the study of the size effect, we wanted to have thin films. Why thin films? Because if you have the bistability, if you have the hysteresis, if you know how to switch them by light, if you know the spatio-temporal process, you need now the thin films in order to integrate them into devices. Okay? So then the thin film period started, and then of course, the question for the thin films, there is many people who try to make thin films. And the question for the thin films, if you take molecular system and you try to fix it on the surface, you have, of course, interactions between the molecule and the surface. And then because the bistability is quite fragile, always you may lose the hysteresis loop because you destroy, the molecule is quite disturbed. And then we thought to make some soft chemistry in order to make these thin films and in order to maintain bistability and to obtain the thin films with hysteresis loop. Okay? So then we took this system here, the 3D polymeric coordination system here. If you look to the KT as function of temperature, you have hysteresis. If you look to this system, you see here, you have the pyrazine connected through the iron by nitrogen. But we know in chemistry that we have another ligand, which is mercaptopyridine system, where you have exactly the same that this ring here, but instead of the iron, you have sulfur. If you have sulfur, that means that you can fix it on gold surface, and you can try to make layer by layer sequential synthesis in order to construct your system sequentially by fixing the first ligand on the gold surface. So we tried to do this. So then we did the layer by layer synthesis. First step is to fix the mercaptopyridine on the gold surface, and then iron salt, and then the platinate here, and then we come back with pyrazine. If you turn here, as the number of the cycles, you can grow your film. Okay? And then when we use this technique, we could have very nice thin films here, okay? And then we could also, by controlling the temperature of the film, the concentrations, etc., all the chemical parameters, we could have films with even 7 angstrom roughness. This is very nice because that means that we can have film and then we can have very low roughness for the applications, okay? So then this was also an important step, okay, in the field, because we have the thin films and we have very flat and with low roughness films. That means that we can use nanotechnology techniques to combine the layer by layer technique we have used by E-beam lithography in order to have dots, okay? So then we did this. What you can see, we can have thin films, spin crossover thin films with very well organized dots, and each dot has low spin, high spin conversion, and then it has its 2 states. Okay? So then this is a kind of hard disk molecular for molecular storage. It's already patented, and we are using it to make memories at very low dimensions. Okay? So then, of course, by E-beam lithography, we can play with the shape, the size of the dots. Even we can have lines here for optical applications. And then the question for us was to see to measure what is the property of only one dot. Okay, you see in magnetism, one dot here, 30 nanometer dot here, switching between spin 0 and spin 2, the change of the magnetization is very small. This means that there is no machine can measure just one dot. Okay? So then we thought about what protocol we can use in order to measure the property of one dot. So then we used chemistry for this, and then the period, hybrid system period started, okay? And then the idea is the following. We wanted to combine the spin crossover system and luminescent rhodamine complex here. Why rhodamine? Because rhodamine, as you know, is emitting in the green region. If you look at the optical properties of the spin crossover, you see that the low spin state absorbs in the green region here. But the high spin form is transparent, there is no absorption. That means that if you combine these 2 complexes, spin crossover and rhodamine 1, that means that if you are in the low spin form, the light of the rhodamine is absorbed, the green light is absorbed, but if you are in the high spin form, there is no absorption. That means that through the spin crossover by temperature, you expect to switch the luminescence of the rhodamine. Okay? So then we did this experiments here. So then the same protocol, we added the rhodamine here in the nanoparticle in order to use this phenomenon. So Lionel got 10 nanometer nanoparticles of such hybrid systems, and then we did the experiments. So then we took exactly the same dose like before, but in this case we have the rhodamine in the dots. You see here we are at 5 degrees Celsius. The system is in the low spin. It's nearly dark, so then the light here is absorbed. Spin crossover, it's around 50 degrees here. So you see that if now we increase temperature to have the spin crossover, you see here, okay, around 50 degrees, when we have the switching between low spin to high spin, you have also, okay, you see, so light is released, so then it's not absorbed, so then we have quenched the luminescence through the spin crossover through this. Okay, so then that means that synergetic effect between rhodamine and spin crossover is possible. You see that through by temperature, by switching, by having spin crossover, we can quench the luminescence, and then we can control the luminescence by switching the system by temperature. This is not the right curve of the dots, but the curve of one dot is something similar to this one, where we have shown also that in one dot you can have the spin crossover through the analysis of the luminescence, and you still have the hysteresis loop. Okay, so now of course you can guess that there is many applications using this effect. For example, in the nano thermometry devices. Here we have a demonstrator to this. Here we took a wire, okay, conductive wire, where we put current in the wire by this board here, okay. We go from 0 to 15 milliamps. That means that we are so that heating the wire here to make the switching from low spin to high spin. Because we put the rhodamine in, you see when the system is in the low spin, it's dark, but when it's in the high spin, you see the luminescence here. That means that you can follow the change of temperature as function of time, as you can see. But what you can see also here, we took several wires here and our film here. You see that spatially you can reveal the value of the temperature. That means that just by following the luminescence here, you can, at the nanometric scale, follow the value of the temperature through the measure of the luminescence. And this has many applications in nanoelectronics or in electronic devices, and even in biology, where people, they need to know the value of the temperature at, with the spatial resolution at the nanometric scale. Okay? So, and then, of course, after this, in this field, the integration, the device integration started, because as I have shown you, now we have the molecules, we have the films, we have the nanoparticles, we have the way how to switch them, okay? So then we have the thin films, which is quite important, and then we wanted now to use these materials into devices. So then, as I told you before, by playing with the concentration of micro-missile techniques, you can have nanoparticles, and then you can play with the shape of the nanoparticle. You can have squares, you can have even rods like that, okay? If you take these rods systems, we can then, by using the electrophoresis synthesis, that means that you do your synthesis in the presence of electrical field, so that you can organize your rods between electrodes. If you do well your protocol, so then you can even select one nanorod here and measure the transport of your rod and the electrical properties. And then we did this, what you can see. You see, as function of the current and temperature, you can see that you have a beautiful hysteresis loop here at room temperature of the current. That means that we can use the electrical properties of the systems for reading the information after integration. Okay? The second application is the optical applications. As I told you in the beginning, the switching can be obtained by temperature, by pressure too, by light. You can by light switch the system from low spin to high spin. And then we use this thin films strategy in order to have junctions. Here, what you can see, we have our spin crossover film, and then we have aluminum here and ITO, and we try to see the properties of the spin crossover film, and then the transport through this junction. If we take this 30 nanometer junction here, you see that very quickly, for example, in this experiment here, if you are at in dark, at low temperatures here, okay, low spin form, if you irradiate your systems, you have photocurrents like that in the low spin state, okay? And then if you continue irradiating the system, you have switching from low spin to high spin by light. That means that here you have the high spin form in the irradiated state. That means that you can compare the photocurrent between the low spin and the high spin. What you can see is that the value of the photocurrent is not the same in the high spin and the low spin state. That means that the transport in your systems depend on the spin state, which is exactly the definition of the spintronic property. Okay? Here you have molecular spintronic properties. That means that the transport, the electrical transport in your systems depends on spin state of the system, which is very, very nice this also, because as you know, Albert Fert discovered the spintronic in semiconducting systems and giant magnetoresistance, etc. And here you have kind of the same effect at the molecular level. Okay? So this is so then one very nice way to go to molecular spintronic and try to make electronic devices. So the last application is mechanical application. As I told you in the beginning, when you go from low spin to the high spin, you have a volume change. Okay? We have volume change at the molecular level. We wanted to see if we can exploit this volume change. You have switching by temperature, molecule going from low volume to high volume. Could we use this volume change in order to make devices, mechanical motors, for example? So then, if you look in classical way by X-ray diffraction, this molecule here, you see that when you measure the crystallographic properties, this is the low spin, and this is the high spin. And this is the volume cell. You see that the volume cell of your system changes by 13%. Okay? And then what we said that if we take our rods here, in principle, if we combine our rod with, for example, gold surface here, to have bilayer, you will have a bilayer like that. You have one part which wants to change its volume, and the other one which is gold, which has same dimension. That means that if you switch your system from low spin to high spin, change volume on only one part of the layer. Okay, on only this part here, you have change of the local distances here. That means that as function of the crossover of the temperature, you expect to have the actuation. Okay? So then on the paper we expect, when we have the crossover, we expect to have this. Okay? Because just because you have a bilayer, one layer wants to change its volume, the other one it's constant. So then you expect that when you have the crossover to have theoretically this actuation. Okay? So then we did this experiment, as you can see here. So then we fixed our bilayer on substrate and we changed the temperature to have the crossover. And you see the actuation follows very well the change of temperatures. So then we are converting temperature into mechanical motion. What is important here is that you can control the direction of the motion by changing the temperature. And then, of course, the idea is the following: by changing, by having this actuation as function of temperature, light, or magnetic field, you can generate controlled motion. Okay, that means that you are converting energy, thermal energy or light energy into motion in a controlled way. So then, of course, we tested this experiment as function of light. You see, dark and irradiation, you have your actuation. That means that if you send several photons fluctuating light, you expect to control the actuation of your system at microscopic or nanometric scale. And this is another experiment here. You see, this experiment has been done by a Mexican PhD student, okay, in the group. Okay, it's a very recent result here. What you can see here, you have the same actuation, okay, when you change your current, so then the temperature, you have your actuation. You can control the actuation of your rods. Okay. What is interesting here is that, for example, you can see that the system goes from yellow to pink. Okay, yellow to pink. That means that you have your actuation, and you have your sensing. You can see where you are by your optical properties. You have the change of you have the actuation, and then the optical, the color change at the same time. That means that you have the actuation, and then you have the sensing at the same on the same materials at the same time, and then that means that you have a protocol for making artificial muscles. Because an artificial muscle, you need the actuation, and you need to sense in which position you are. Okay? So then, of course, by another Mexican PhD student, we studied the properties, the mechanical properties of these systems, and then we used IFM techniques to measure the elastic properties of spin crossover materials to see if they are good to make real machines. Okay, so then she uses the IFM techniques to measure the Young modulus. What you can see when you go from low spin to the high spin form, you have the Young modulus changing by 30%. So that if you have such change, if you plot now on the table here the work density, here it's the spin crossover materials, here is the human materials, you see that these materials have very nice work density. Okay? And then if you look as function of the size of your system, in the macroscopic scale, they behave like human muscles. But at the nanometric scale, they are very quick. They can be very quick, even at 100 kilohertz fluctuation. Okay? Actuation. So that means that these systems can be really used as artificial muscles in very efficient way. And then we tried to make this muscle. What we did, so then we took just polymer where we dispersed in it the nanoparticles, and then we took here a wire, okay? So then the wire where you can send your current, you have the heating between two contacts here, and we put our film around the wire. What you can see, okay, this wire is macroscopic scale, centimeter scale. You see that when you send your fluctuation current, so then changing of temperature, you see that you can clearly have your muscle, your actuation in controlled way. We are just in this point today, so then we are continuing working on this field. And then the idea, of course, is to try to integrate these systems to repair some defects in human bodies, okay? Like what Japanese they are doing here. We expect also to integrate our materials in order to make some human reparations in the artificial muscle way. So then we also are working on NEMS techniques, okay? You know the NEMS, it's nano or micro electromechanical systems. What you can see very quickly is that when we put film, spin crossover film on the NEMS, you can have the effect of the spin state on the activity of the NEMS or the NEMS, and then we will have also some very nice applications in the field of NEMS of this. So, just to tell you that, as you can see, the combination between chemistry, physics, nanotechnology, and theory, we can deal with very exciting field, very exciting spin crossover systems in order to have future generation devices. Thank you very much for your attention.
Well, maybe if you have many questions, currently we have time for some questions, and after this, if someone of you wishes to talk to Professor Azzedine, he will be here for some minutes, please So, any questions? Romero?
Yes.
Thank you for such a wonderful talk. When you mentioned about this expansion, the first thing that I thought was the electrics. But I see that you already are working to that direction, right?
Yes.
So that means that you can have now these very tiny things that you can move.
Yes.
Because these electrics in general are large compared to your devices, right?
Yeah.
So these piezoelectrics, how much can you expand it? Is it still like around 10% or?
Yeah, it is. It is a little bit less. 6-5%.
And then the hardness is just around the same number that you mentioned?
Yes.
So that means that they can push into matter?
Oh, yeah. Yeah, of course. That's the way we are doing.
So you can have this micro sort of,
yeah. We are doing it, yeah. We are trying to. Oh, yeah, of course, yeah. We are trying to do it in that way, yes.
Okay.
So all these results of the actuations, it's something like 1 year work. That's all. It just started. There is no systems showing this kind of actuation in this field, of course, in the Spintronic. And then there is many ways. You can even combine the actuations and the Spintronic too. Because you have spin state changing the electrical properties and the volume. You can combine them. And then in the same count, you have also the color change. And then we can also try to combine the elastical properties with photochromic properties in order to see also some hybrid properties which could be combined in order to go to some clever or smart control of these systems by light or by electrical field.
And the repetition rate is quite high, right?
Sorry?
The repetition rate, I mean the...
Oh, it can be very high.
No frequency of...
There is no fatigue, because in chemistry we say in this system they have no corrosion, because the crossover, it's intramolecular. There is no exchange of energy between this system and external systems. So there is no corrosion. You can have repetition as you wish.
Any other question?
How do you find, if we're interested in your participants, we actually some applications in the real world, what you have added?
So for the moment, so then all the elastic properties, the mechanical properties, for the moment, we are just making the fundamental approach. Okay, for the moment, we are quite far from the real applications. We are on the way. We are just starting with new field. Okay, but for the electrical properties and the optical properties, like for example, I have shown you the grating, optical grating. Okay. We have seen, I did not show the results here, that if you have any gas in your atmosphere interacting with this polymer, you can have the change of spin crossover. If you have change of spin crossover, you have the change of the optical properties of the material. That means that through optical diffraction, through the grating, you can detect your gas. Okay, so then we are trying to have demonstrators with industrials as sensors for gas, and then we have also some other applications, some other industrial applications concerning displays, intelligent displays, and.
Just a question. How do they compare with standard fiber optics sensors, the gas sensors?
The difference is which gas you detect. Okay, these systems can detect few gases which are very important for domestic life, etc., which cannot be detected by standard sensors. That's the point. Okay. This is the important point, is the sensitivity to molecules which are not detected by the common sensors. That's the difference. And in our case, we can play with chemistry in order to fix the hysteresis and the position on the crossover, and then we can fix which molecule we wish to detect, and then you have some selectivity which cannot be obtained by standard sensors. That's the point. And then we have also applications of course, at the beginning, we started by memory effect, like because we have dots, then we can have our film, and then we have crossbar, then you can at the intersection read the electrical capacity, okay? And then you can read your information electrically. And then in this way too, we have the pattern, and then we are looking some industrials in order to build new generation of memories. With only memories which can be quite stable and that can be interesting for application in space.
Any other question? Comment? Gabriel?
Yeah.
What about the, I don't know if you are working in changing the temperature in which the process happens.
Yes.
So, because there is a big range in which you can make the process, right?
Yes.
So are you working on that and
Oh, yeah.
producing different kind of materials? Or
Yeah.
or what is the strategy to?
Oh yeah, the strategy is only chemistry, okay? Because you know, the spin crossover is ligand-filled process, okay? The ligand-filled, that means that around your ion, you need to control the coordination sphere. And then the critical temperature of the switching depend on the ligand field. That means it depends on the ligand you are putting around your ion. So then by playing with changing the ligands around the ion, you can change your critical temperature. Today we have changes from, let's say, nitrogen temperature till 400 kelvins. Okay? You have many possibilities to fix the temperature just by changing the ligand field around the coordination sphere. This is the chemistry part of the group. And then we have a large range of large interval of temperatures you can reach by just changing the ligands.
Any other comment? Question? Well, if someone of you, once again, wish to talk for some minutes with Professor Azzedine, and also, I forgot the beginning of the talk, is also with us Dr. Lionel Summer from the same group. Maybe you can also talk to Dr. Lionel. Furthermore, you already have all the information in order to contact Professor Azzedine and his group. So, thank you, and let's thanks again the talk of Azzedine.